In the profound quiet between the stars, where the darkness is not merely an absence of light, but a substance of its own, there moves a shape of perfect nothingness. It does not announce itself with blazing accretion disks or brilliant jets of relativistic plasma. It travels silently, a solitary mass bending the fabric of space, time around it as it passes, a ghost in the celestial graveyard. This is the story of the wandering black hole, an isolated gravitational singularity adrift in the interstellar medium. And its discovery did not come from witnessing the thing itself, for a black hole, by its very nature, is the universe's most definitive secret, but from observing, over years of patient measurement, the subtle, haunting distortion of a single point of light far behind it. To understand this discovery is to engage in a form of cosmic detective work, where the clues are not objects, but the bending of space and the stretching of time, where the evidence is written in the minute deflections of starlight traveling for millennia across the galactic plane, only to be subtly redirected at the last possible moment by an invisible, moving mass of terrifying gravity. The narrative begins not with a bang, but with a slow, meticulous anomaly in a vast field of data. A single star that began inexplicably to brighten against the immutable backdrop of the Milky Way's disk, its light magnified and stretched by an effect predicted by Einstein's general theory of relativity over a century ago, but never before caught in the act of being caused by such a small, dark, and lonely object on the move through our galaxy. This effect is gravitational microlensing, a delicate and rare astronomical phenomenon that occurs when a massive object passes almost perfectly between an observer on Earth and a distant source star. Unlike the dramatic lensing caused by immense galaxy clusters that warp the light of entire galaxies into arcs and rings, microlensing is a subtle, transient event. The foreground object's gravitational field acts as a lens, curving the space-time around it, and thus bending the paths of the background star's light rays. This bending concentrates the light, causing the star to appear to temporarily brighten a spike in its luminosity that can last for days, weeks, or months, depending on the mass of the lens and the relative motions involved. For decades, astronomers have used this technique to search for dark, compact objects within the Milky Way, cataloging thousands of events, most of which are attributed to common stars, both faint and bright. Yet within this catalog lay a peculiar subset of events where the lensing signature was strong and clear, but where follow-up observations with the most powerful telescopes available could find absolutely nothing at the lens's location. No star, no brown dwarf, no trace of infrared or optical emission. These were ghost lenses, events pointing to massive, dark bodies. And among these, one event stood apart for its duration, its signature, and the exquisite precision of its measurement. The event, designated MOA 2011BLG191, Ogle 2011 Blog 0462, was detected independently by two microlensing survey projects, the Optical Gravitational Lensing Experiment, OGLE, and the Microlensing Observations in Astrophysics, MOA, collaboration. For over 270 days, a star in the direction of the galactic bulge, some 26,000 light-years away, grew steadily brighter, peaked, and then faded back to its normal state. The sheer length of the event immediately signaled that the lensing object was massive. The duration of a microlensing event is proportional to the square root of the lens's mass. Preliminary analysis suggested a mass roughly 7 times that of our Sunday. Yet, when astronomers pointed the Hubble Space Telescope toward the location years later, expecting to see the faint, reddish glow of a low-mass star responsible for such a long lens, they saw nothing. The Hubble data was precise, ruling out the presence of any normal star down to an extraordinarily faint limit. The lens was dark and it was moving. The telltale signature was in the astrometric shift, the apparent change in the background star's position on the sky caused by the deflection of its light. As the invisible lens moved, it shifted the apparent position of the background star in a tiny but measurable way. This astrometric microlensing signal, a deflection of just a few hundred micro-arcseconds, a shift equivalent to measuring the width of a human hair from over a mile away, was the key that unlocked the nature of the object. The magnitude of this shift, combined with the long event duration and the total absence of light, pointed conclusively to a single, isolated stellar mass black hole, drifting through interstellar space at a velocity of about 45 kilometers per second. To contemplate such an object is to confront a profound outcome of stellar evolution, a corpse left behind after the cataclysmic death of a massive star. When a star many times more massive than the Sun exhausts its nuclear fuel, its core collapses under its own weight. In a supernova explosion of unimaginable power, the star's outer layers are blasted into space, enriching the cosmos with heavy elements. What remains of the core, if it is between roughly 3 and 20 solar masses, continues its collapse unchecked, crushing itself into a region of space so small and dense that not even light can escape its gravitational pull. A black hole is born. Conventional astrophysics suggests that such an event is not gentle. The supernova explosion is thought to be asymmetric, imparting a natal kick to the newborn black hole, much like a neutron star receives a kick that sends it hurtling through space as a pulsar. This kick, a product of violent recoil from unevenly ejected material and neutrinos, can be powerful enough to eject the black hole from its birth cluster or even from the galactic disk entirely, sentencing it to an eternal, solitary journey through the void. The wandering black hole, therefore, is not an anomaly, but a predicted inhabitant of the galaxy, a silent testament to the chaotic and forceful nature of stellar death. Yet, for all the theoretical predictions, one had never been definitively caught, isolated and dark, until this painstaking analysis of a single, slowly brightening star revealed its invisible passage. The isolation of this object is what grants it a peculiar, almost philosophical weight within the catalog of known black holes. We are accustomed to thinking of these gravitational phenomena in terms of their relationships, the binary partners locked in a fatal dance, their inward spiraling revealed by the chirping gravitational waves sensed by LIGO and Virgo, the supermassive beasts that squat at the hearts of galaxies, their immense appetites powering brilliant quasars and active galactic nuclei. Even the stellar mass black holes, often found with a companion star, siphoning material from it to form a visible, swirling accretion disk of superheated plasma that glows in X-rays. But here, in this detection, we find a singularity without a partner, a gravity well without a visible source of infall, a conclusion to a star's life that results not in a centerpiece, but in a wanderer. Its solitude means it interacts with the universe in the most minimal, most fundamental way possible, purely through gravity. It does not shred stars. It does not emit jets. It does not warp the cosmos on a grand scale. It simply is. And its being warps the paths of photons that pass too close, a silent and continuous testament to the fact that gravity is the geometry of space-time itself, and that a mass, even an invisible one, writes its signature upon that geometry for any careful observer to read, if they know how to look for the faintest of imprints. To measure such an imprint required not only technological prowess, but a profound patience, a willingness to wait for the universe to perform its slow alignments over distances that defy human comprehension. The microlensing event itself unfolded over the better part of a year, a leisurely brightening and fading against the tapestry of the galactic bulge. But the true work began years later, with the Hubble Space Telescope. The challenge was immense. To measure the infinitesimal shift in the apparent position of a single ordinary star 26,000 light-years away, a shift caused by the gravity of an object we could not see, which had already moved on from its moment of perfect alignment. This is the realm of precision astrometry pushed to its absolute limits. Hubble, free from the distorting shimmer of Earth's atmosphere, observed the star not once, but 6 times over 6 years. Each observation was a meticulous exercise in calibration, using the star's neighboring, unchanging background stars as a fixed reference grid against which its tiny, telltale wobble could be charted. The wobble they sought was the residual deflection, the ghost of the lens's passage still lingering in the star's photographed position. It was a deflection of about 0.2 milliarc seconds. To grasp the scale of this measurement, consider that a milliarc second is the angular size of a dime on the surface of the Moon. As viewed from Earth, the team was measuring a fraction of that, a displacement so small it strains the very concept of measurement. That they succeeded is a triumph of instrumental stability and statistical analysis, a whisper of data extracted from a sea of cosmic noise. The analysis yielded more than just confirmation of a black hole. It provided a rare and precise set of parameters for this dark wanderer. The lensing models, fed with the photometric light curve from the ground-based surveys and the astrometric shift from Hubble, converged on a mass of approximately 7.1 solar masses. This places it firmly in the expected range for a black hole formed from a collapsed stellar core. Its distance was pinned to about 5,150 light-years from Earth, making it one of the closest known black holes, a surprisingly nearby ghost. Its proper motion, its speed across our line of sight, was calculated to be around 45 kilometers per second. This velocity is a clue to its origin story, a fossil record of its violent birth. A kick of that magnitude is consistent with models of asymmetric supernova explosions, where the collapsing star's outer layers are ejected more forcefully in one direction, rocketing the newly formed compact remnant in the opposite direction, like a celestial cannon recoiling. This event likely hurled the black hole out of its natal stellar nursery, severing any gravitational bonds with sibling stars and setting it on its current lonely trajectory through the galactic disk. We can imagine then, not just the object as it is now, but its history, a massive star, born in a cloud of gas and dust, living a short, brilliant life before ending in a convulsive explosion, its core vanishing from the visible universe, its legacy a silent, speeding knot of warped space. The discovery of this isolated black hole opens a new window onto a hidden population that is believed to be vast. Theoretical estimates suggest that the Milky Way should be home to perhaps 100 million stellar mass black holes, the remnants of the most massive stars that have lived and died over the galaxy's long history. The vast majority of these are expected to be isolated, dark, and drifting. Until now, we have only been able to census the small fraction that are in binary systems and actively accreting, or the merging binaries we detect via gravitational waves. This solitary wanderer is therefore a crucial data point, a direct detection of one member of this silent majority. Its mass, distance, and motion are pieces of a statistical puzzle. By finding more of these ghosts through microlensing, and future missions like NASA's Nancy Grace Roman Space Telescope are designed to find thousands, astronomers can begin to build a true demographic picture of black holes in our galaxy. They can test models of stellar evolution and supernova mechanics by studying the distribution of their masses and velocities. They can probe the intricate question of how many black holes received powerful kicks and how many may have formed in situ, perhaps even retaining a slow, sedate motion that belies a less violent departure from their stellar origins. Each isolated black hole detected is a fossilized moment of stellar death, and collectively, they form a forensic record of the galaxy's most dramatic transformations. But the implications ripple outwards, beyond stellar corpses and galactic demographics, into the very fabric of cosmic understanding. The successful use of astrometric microlensing to weigh and pinpoint an invisible object is a stunning validation of general relativity, as a practical tool for celestial measurement. Einstein's equations, conceived in the realm of thought experiments and profound theoretical insight, are here used as a precise scale and a tracking device for the darkest objects in creation. Furthermore, this discovery touches upon the enduring mystery of dark matter. While black holes of this mass are not considered a primary component of the dark matter that holds galaxies together, their formation, history, and abundance don't match the required cosmological profile. The technique itself is a prototype for searching for any massive compact halo objects, or MACOs, that might lurk in the galactic outskirts. The ability to find isolated, dark masses drifting through the galaxy is fundamentally the ability to take a census of all massive compact objects, regardless of their luminosity. It turns the galaxy into a vast laboratory, where gravity itself is the only probe needed, where light is not a requirement for discovery, only its subtle deflection. As we peer deeper, we may yet find that the darkness between the stars is not empty, but richly populated with the unseen residues of cosmic events, a shadow population whose existence is written only in the bent paths of ancient starlight. As the data settled and the analysis crystallized into a firm scientific conclusion, one could not help but engage in a slower, more reflective line of thought to follow. In the mind's eye, the journey of this particular knot of space-time itself. Projecting its current motion backwards through the Milky Way's gravitational potential, astronomers could trace a possible path, a ghostly orbit through the galactic disk that might hint at its origins.
Its velocity, while substantial, is not enough to eject it from the galaxy entirely. It is bound, as are all stars and stellar remnants in the disk, to the immense gravitational hold of the galaxy's total mass, most of which is the invisible shroud of dark matter. So it wanders, but within confines, following a slow, looping trajectory around the galactic center that will take hundreds of millions of years to complete. It will pass through the great spiral arms, through clouds of molecular gas and regions of recent star formation, through the thin haze of the interstellar medium, all without interaction, a submarine moving silently through a deep ocean, its presence felt only by the most delicate of instruments aimed at just the right moment. For millennia upon millennia, it will be alone, its gravity imperceptibly perturbing the paths of dust grains and the occasional lone planetesimal that might drift too close, a shepherd of darkness whose flock is the unseen. The environment through which it travels is not a perfect vacuum, but a region filled with the tenuous filaments of the interstellar medium, a mixture of gas, mostly hydrogen, and fine dust. A black hole of this mass, moving at such a speed, will interact with this medium in subtle ways. As it plows through the hydrogen, its immense gravity will pull and compress the gas ahead of it. However, without a companion star to provide a steady stream of material or a dense enough region like a molecular cloud to force significant accretion, this process is extraordinarily faint. Theoretical models suggest that an isolated stellar mass black hole moving through a typical region of the interstellar medium might accrete matter at a rate billions of times slower than a black hole in a binary system. The infalling gas would be so sparse and the relative velocity so high that it would not have time to form a coherent, hot accretion disk. Any emission produced would be negligible, likely in the far ultraviolet or very soft X-rays, and drowned out by the background glow of the galaxy. It is the epitome of quiescence. Yet, there is a possibility, a slow, almost geological possibility. Should this wanderer's path ever lead it directly into a dense molecular cloud, a stellar nursery brimming with gas, the story could change. The black hole could begin to accrete more substantially, perhaps lighting up faintly as material spirals in, not with the fury of a binary X-ray source, but with a dim, cold glow that would be the signature of a solitary giant feeding on the raw material of star formation itself. This, however, is an event of low probability over even cosmic timescales. Its destiny, for the foreseeable eons, is one of continued darkness and silence. This profound isolation raises a deeper, more speculative question about the potential for such an object to harbor a system of planets. Could a black hole have planets? The concept seems drawn from science fiction, yet it is a subject of serious theoretical inquiry. The formation mechanism is the crucial puzzle. A black hole born from a supernova would likely see any pre-existing planetary system utterly destroyed in the cataclysm. The explosion and the subsequent loss of the star's mass would destabilize orbits, flinging planets into the void or vaporizing them. However, there are alternative, slower pathways. A wandering black hole could, over time, gravitationally capture free-floating planets, rogue worlds that have themselves been ejected from their parent star systems. The vast population of such interstellar planets is now thought to be enormous, perhaps outnumbering stars in the galaxy. A close encounter between a black hole and a rogue planet, where the planet loses just enough kinetic energy to become bound, is statistically unlikely but not impossible over billions of years. The resulting system would be utterly bizarre, a planet orbiting in absolute darkness, warmed not by starlight but perhaps by the faint glow of accretion or by tidal forces within the planet itself. Its sky would be a tapestry of the galaxy's stars, warped and lensed by the black hole's gravity, with the central presence marked only by a perfect circle of blackness blotting out the starlight behind it, ringed perhaps by a ghostly Einstein ring of distorted background galaxies. It is a chilling, beautiful thought, a world whose sun is an absence. The discovery of this first clear isolated black hole is less an ending and more a beginning, a proof of concept that illuminates the path forward for a new era of gravitational detective work. The tools that found it were, in a sense, repurposed. Hubble was not built for this specific task, and the ground-based microlensing surveys were optimized for finding exoplanets and low-mass stars. The future, however, holds instruments designed with such dark wanderers in mind.
The Nancy Grace Roman Space Telescope, slated for launch later this decade, carries a primary mission that includes a vast microlensing survey of the galactic bulge. With a field of view 100 times larger than Hubble's, and the ability to monitor hundreds of millions of stars with exquisite precision, Roman is expected to detect hundreds, if not thousands, of microlensing events caused by isolated compact objects. Its data, especially when combined with parallax measurements from the Gaia mission, will allow for mass and distance determinations with far greater efficiency and in much greater numbers. Each detection will be a data point on a graph, slowly filling in the mass function of stellar remnants. Of particular interest will be the lower boundary, the so-called lower mass gap, between the heaviest neutron stars, around 2.5 solar masses, and the lightest black holes, around 5 solar masses. Does this gap truly exist as a desert in the mass distribution, a result of the physics of supernova collapse, or is it simply an observational bias? Isolated black holes discovered through microlensing, which does not depend on the object's electromagnetic emission or its presence in a binary, offer a clean, unbiased way to answer this question. Furthermore, the population of higher mass black holes, those upwards of 10 solar masses, will tell us about the lives and deaths of the galaxy's most massive stars, whose evolution is complicated by factors like metallicity, rotation, and binary interactions. Beyond Roman, the future of astrometry promises even sharper vision. Missions now in early planning stages, such as the European Space Agency's Theia concept, aim to measure star positions with nanosecond of arc precision, an improvement of several orders of magnitude over even Gaia. With such stupendous accuracy, the astrometric signature of a passing black hole would not be a subtle wobble requiring years of observation to confirm, but a clear and distinct signal detectable in near real time. The galaxy would, in a sense, become transparent to gravity. Every dark mass above a certain threshold moving through the galactic neighborhood would leave a rippling track in the observed positions of the background stellar field, a wake of distorted spacetime that could be charted and followed. We would move from discovering the occasional, fortuitously aligned wanderer to mapping the flow and distribution of dark, compact objects throughout the galactic disk, understanding their kinematics and origins, as plainly as we now study the motions of visible stars. This is the ultimate promise of the technique validated by this first lonely black hole: to see not with light, but with the curvature of space itself, to perceive the galaxy's hidden skeletal structure of mass, both luminous and dark. In this future, the cosmos reveals itself not only through the photons it emits, but through the indelible warps it creates in the fabric of reality, a deeper and more fundamental language written in geometry. The contemplation of this solitary object inevitably draws us inward to consider not only its journey through space, but the nature of its interior, the singularity it conceals. The black hole's event horizon, the point of no return for this particular wanderer, is a sphere with a radius of roughly 20 kilometers, a space so small that it could fit within a modest city. Yet within that boundary lies a gravitational gradient so extreme that the laws of physics as we know them are stretched to breaking point. At the horizon, the escape velocity equals the speed of light. Crossing this threshold, matter and energy are lost to our observable universe, their information sequestered behind a perfect one-way membrane. What happens beyond is the realm of quantum gravity, a domain where general relativity's smooth geometric fabric is presumed to dissolve into a froth of uncertainty, and where the singularity, a point of infinite density, likely resides. This is not merely an abstract concept, but a physical reality for this 7 solar mass object, a reality that is forever hidden from us, its secrets locked away by the most absolute prison ever conceived by nature. The wandering black hole carries this mystery within it as it travels, a self-contained enigma, a universe in itself that is decoupled from our own, governed by rules we can only guess at through the tentative equations of theories yet to be proven. This inherent mystery connects the discovery to one of the most profound theoretical debates in modern physics, the black hole information paradox. Formulated by Stephen Hawking in the 1970 seconds, the paradox arises from the conflict between quantum mechanics and general relativity. Hawking radiation, the theoretical process by which black holes can slowly evaporate over astronomical timescales, suggests that a black hole can eventually disappear, radiating away its mass. Quantum mechanics insists that information about what fell into the black hole cannot be destroyed. Yet the Hawking radiation appears to be purely thermal, carrying no information about the infalling matter. Where then does the information go? For our isolated black hole, this is not an immediate practical concern. Its evaporation timescale is orders of magnitude longer than the current age of the universe. But it is a fundamental question about the ultimate fate of whatever it may have accreted, however minutely, during its long journey. The black hole is, in this light, not just a massive object, but a quantum informational puzzle box. And its isolation makes it a purer laboratory for such thought experiments than its bustling, binary cousins. It is a closed system, its inputs from the interstellar medium vanishingly small, its outputs non-existent in any electromagnetic sense. It is the closest thing in nature to a perfect thermodynamic entity, a sink of entropy, and a challenge to our understanding of how the universe preserves its past. From the quantum scale of its hidden interior, we pull back once more to the galactic, considering the broader population to which this wanderer must belong. Statistical extrapolations from this single detection, combined with the known efficiency of microlensing surveys, allow astronomers to estimate the number of such isolated stellar mass black holes in the Milky Way. The figures are staggering, suggesting a population numbering in the tens of millions, perhaps even approaching 100 million. This silent multitude forms a kind of gravitational substrate woven through the galaxy's disk and halo, an unseen architecture of mass that contributes to the overall gravitational potential but reveals itself only through rare, precise alignments. Their distribution is not uniform. They should trace the past locations of star formation, following the spiral arms and the galactic bulge, though their natal kicks will have scattered them widely over time. They are the dark echoes of the galaxy's most massive, short-lived stars, and their collective gravity subtly influences the motions of visible stars and gas clouds. They are, in a tangible way, part of the galaxy's hidden history book, their masses and velocities encoding the conditions of the galaxy's earlier epochs, the metallicity of the gas from which their progenitor stars formed, and the violence of stellar death across cosmic time. The search for these objects now becomes a deliberate, systematic pursuit, a new frontier in observational astronomy. The methodology pioneered with this detection provides the blueprint. It requires a synergy of time-domain photometry, the continuous, long-term monitoring of star fields to catch the slow brightening of a microlensing event, and high-precision, follow-up astrometry to measure the lensing object's mass and confirm its darkness. This is a task perfectly suited to the coming era of synoptic surveys. The Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, beginning later this decade, will scan the entire southern sky every few nights, discovering thousands of transient events, including microlensing. While its primary mirror is ground-based, limiting its astrometric precision compared to space telescopes, its unparalleled survey speed and depth will provide an immense catalog of candidate events. These candidates can then be passed to space-based observatories like Roman, Hubble, or James Webb for the critical follow-up observations that can separate black holes from faint stars and brown dwarfs. This collaborative, multi-observatory approach turns the entire astronomical community into a network of detectives, each instrument contributing a piece of evidence to build a case for the identity of each dark lens. Amidst this technical and scientific narrative, there persists a quieter, more reflective strand of thought, a consideration of the existential loneliness embodied by the object. In a universe that seems to favor systems, binaries, clusters, and galaxies, an isolated black hole is an outlier of solitude. It is a product of a violent birth that severed all connections, a gravitational entity that interacts with the cosmos only through the most impersonal, universal force. It emits no light, creates no solar wind, fosters no chemistry on orbiting worlds. It is a monument to silence and endings. And yet, in its very isolation, it holds a unique purity. It is a laboratory uncontaminated by the complexities of binary interactions, a clean test of gravitational theory, a direct manifestation of mass-warping spacetime. Its value to science is precisely because of its solitude. As we on Earth, connected to each other and to our life-giving star, strive to understand the cosmos, we find ourselves peering into the abyss of this disconnected wanderer, seeking to comprehend a state of being so alien to our own experience of connection and interaction. It challenges us to think in terms of pure gravity, pure geometry, and the ultimate fate of matter when it is removed entirely from the realm of light and information exchange. The wandering black hole, in its profound and endless journey, becomes not just an astronomical object, but a metaphor for the ultimate isolation possible within a connected universe. A dark mirror held up to our own place in the cosmic web. The path of this dark wanderer, while lonely, is not without potential for future, distant interaction, a narrative that unfolds on timescales that dwarf human history. Its current trajectory, as best as can be reconstructed, suggests it will spend the next millions of years traversing the relatively quiescent regions of the galactic disk. But the Milky Way is a dynamic, evolving entity. Spiral arms rotate, density waves sweep through the interstellar medium, and the gravitational pull of passing giant molecular clouds can gently perturb even a 7 solar mass object. Over hundreds of millions of years, its orbit will be sculpted by these broader galactic forces. There is a minute probability that its path could one day intersect with a stellar binary system. The gravitational dynamics of a close encounter between a black hole and a pair of stars are complex and chaotic. Possible outcomes include the disruption of the binary, the capture of one star by the black hole to form a new, violently interacting binary system, or even a gravitational slingshot that ejects one or all of the bodies at high speed. Such an event, while extraordinarily rare, would fundamentally alter the nature of the wanderer, ending its long solitude in a burst of dynamical fury and potentially giving rise to an observable X-ray source, a second act in a life cycle that had seemed terminally quiet. It is a reminder that in the galaxy, given enough time, no isolation is necessarily permanent. The cosmic dance is slow, but its partners are always moving, and gravitational interactions eventually rewrite every story. The discovery also compels us to look beyond our own galaxy, to consider the intergalactic void. If a natal kick from a supernova is sufficiently powerful, it can eject a black hole entirely from its host galaxy, consigning it to the true abyssal darkness between galaxies. The velocities required for such an ejection are greater than the galactic escape velocity, which for the Milky Way is on the order of 500 to 600 kilometers per second. While the wanderer we have detected moves at a mere fraction of that speed, theoretical models and simulations of stellar dynamics in dense clusters suggest that a subset of black holes could receive such extreme kicks, particularly from asymmetric explosions in binary systems or from dynamical interactions in globular clusters. These hypervelocity black holes would become true intergalactic wanderers, untethered from any galactic structure, drifting through the million-degree plasma of the intracluster medium in galaxy clusters, or through the near-perfect vacuum of cosmic voids. Their detection would be even more challenging, as the density of background stars from microlensing drops precipitously outside the galactic plane. Yet, the possibility exists. They would be the ultimate dark sailors, navigating the immense stretches of nothingness between islands of stars, their gravity perhaps subtly influencing the paths of the rarest intergalactic stars or the faint light of the cosmic microwave background in ways so minuscule as to be currently unimaginable to measure. Their existence speaks to a universe where even the most massive objects can become unmoored, set adrift on the cosmological sea. Closer to home, the presence of a relatively nearby isolated black hole invites a speculative but scientifically grounded question. What would a close approach to our solar system look like? The detected black hole is a safe distance away, but the galaxy's population implies a statistical distribution. The closest isolated black hole is likely within a few hundred to 1,000 light-years. A truly close encounter, within a light-year or less, while vanishingly improbable on any human timescale, is a useful thought experiment to understand gravitational influence. As such an object approached, its gravity would begin to perturb the delicate cloud of comets in the distant Oort cloud, sending a shower of icy bodies inward toward the Sun, potentially causing a period of heavy bombardment on Earth and the other planets millions of years after the black hole's closest passage. Long before that, however, its presence would be revealed not by sight, but by its gravitational effect on the precise motions of nearby stars, and, eventually, on the planets themselves. Astrometric satellites like Gaia would detect anomalous proper motions and parallaxes for an increasing number of stars in a particular region of the sky, all seemingly pulled by an unseen point. As it drew closer, its gravitational lensing effect would become more pronounced, distorting and magnifying the images of stars directly behind it, creating temporary, moving pairs of mirage stars. The Sun's position itself would show a tiny, anomalous wobble. There would be no tidal forces until it was extraordinarily close. The gradient of its gravity across the solar system would be negligible until it was within a fraction of a light-year. The primary signature would be a silent, geometric distortion of the heavens, a crescendo of gravitational lensing effects growing in the sky, a clear and present demonstration of curved space-time wrought by an invisible, approaching mass. It would be a humbling and terrifying spectacle, witnessed not with light, but with the measured displacement of every pinpoint of light in its vicinity. Returning from such speculative shores to the solid ground of present science, the detection of the wandering black hole stands as a landmark in a broader shift in astronomical methodology. For centuries, astronomy was the science of light. We built larger telescopes sensitive to new wavelengths to collect more photons from distant objects. The late 20th and early 21st centuries have ushered in the era of multi-messenger astronomy, where we learn from photons, neutrinos, cosmic rays, and now, definitively, gravitational waves. The detection of this black hole represents a subtle but powerful subcurrent within this shift. It is a discovery made not by receiving a message from the object, but by observing its effect on messages from other objects. It is astronomy via indirect imprint, a study of the negative space. We are learning to read the universe not only by the signals it sends, but by the distortions it imposes on signals passing through it. This is a profound deepening of our observational toolkit. It suggests that anything with mass, no matter how dark, can be found if it bends a sufficient number of well-measured light rays. It turns the entire cosmos into a lensing array, a vast instrument for detecting the otherwise invisible. In this paradigm, darkness is not an obstacle to observation, but a different kind of canvas upon which gravity paints its signature. As we prepare to conclude this exploration, though, the story of this object and its kindred will continue to unfold for as long as humanity looks to the stars. We are left with a resonant, quiet image. Somewhere in the dark, approximately 5,000 light-years away, a sphere of perfect event horizon 20 kilometers across moves at 45 kilometers per second against the background of the galactic core. It warps the starlight from stars 20,000 light-years further on, bending their ancient photons by a fraction of a degree. It does not know it has been discovered. It does not know it is alone. It simply follows the geodesic carved for it by the combined gravity of the galaxy, a path set in motion by a cataclysm long ago. It is a fossil of a star's death, a specimen of pure gravity, a hidden node in the network of mass that shapes the Milky Way. Its discovery is a testament to human curiosity, patience, and our growing mastery of the subtle language of relativity. It reminds us that the universe is filled with quiet dramas, slow-motion events of immense significance that require us to slow our own perception, to measure with exquisite care, and to listen not for shouts, but for the faintest of whispers written in the geometry of space-time itself. The wandering black hole is a solitary note in the cosmic symphony, a deep, sustained bass tone felt more than heard, informing the structure of the music around it, and now, finally, perceived by the attentive ear of science. The enduring scientific legacy of this discovery lies not merely in the identification of a single object, but in the validation of a method that peers into the darkest recesses of galactic demography. With the template now established, the focus turns towards the statistical harvest that future surveys promise, a harvest that will refine and perhaps redefine our understanding of stellar endpoints. Each isolated black hole detected through microlensing provides a precise mass measurement, a crucial data point for constructing the initial mass function of stellar black holes, free from the confounding variables of binary interaction, accretion, or merger history. This is pure remnant mass, a direct echo of the progenitor core. As these data points accumulate into the hundreds, they will map a distribution. Is there a sharp cutoff at the lower end, confirming the mass gap as a real desert between neutron stars and black holes, a testament to the explosive physics that separates a successful supernova from a direct collapse? Or does the distribution smear across this gap, hinting at alternative formation channels like the merger of neutron stars within dense clusters or the collapse of exotic stellar objects? Similarly, the high mass end of the distribution will tell us about the lives of the most massive stars in our galaxy's history. The upper limit for a stellar mass black hole, thought to be around 50 to 60 solar masses due to processes like pair instability supernovae, can be tested against a clean, volume-limited sample. These are not the spectacular, merging black holes seen by LIGO, which may have been forged in different environments or through hierarchical mergers. These are the quiet, individual remnants of single-star evolution, offering a baseline for the galaxy's intrinsic production of compact objects. Beyond mass, the velocities of these wanderers, discernible from the microlensing event parameters and follow-up studies, encode the history of their births. The distribution of kick velocities is a fossil record of supernova asymmetry. By measuring the speeds of many isolated black holes, astronomers can reverse engineer the explosive mechanisms that launched them. Do most black holes receive modest kicks, leaving them to orbit near their birthplaces? Or is a high-velocity tail a common feature, suggesting violently asymmetric explosions are the norm for massive stellar collapse? This kinematic data, when cross-referenced with estimated ages derived from the black hole's positions relative to star-forming regions, can paint a moving picture of the galaxy's stellar death rate over time. It allows us to trace back the wanderers to their likely origins in spiral arms or the galactic bulge, understanding how the galaxy's star-forming activity has scattered its dead throughout the disk and halo. In this way, the population of dark wanderers becomes a dynamic archaeological tool, their masses and motions, the shattered pottery and bone fragments from which we reconstruct the life and death cycles of the galaxy's most dramatic inhabitants. The implications also extend into the domain of planetary science and search for life in its most tenacious forms. While the concept of a planet orbiting an isolated black hole seems the stuff of bleak fiction, the mechanisms for their capture or formation in a post-supernova disk, though highly speculative, have been explored in theoretical papers. Should such a world exist, its conditions would be the antithesis of Earth's. With no sunlight, the surface would be plunged into a deep cryogenic freeze, its only external heat source, the faint glow of Hawking radiation, utterly negligible, or the minute thermal energy from radioactive decay in its core. Any atmosphere would likely condense and snow out onto the surface. Yet, if the planet retained a substantial hydrogen atmosphere, or a deep subsurface ocean heated by tidal forces from the black hole's gravity, or by its own internal geology, the possibility for a biosphere, however alien, cannot be ruled out entirely. Life, as we understand it, requires an energy gradient and a liquid medium. A tidally heated subsurface ocean beneath an ice shell, similar to Europa but in eternal darkness, could theoretically provide both. The energy source would be the gravitational flexing of the planet's interior as it orbits the black hole, and the chemistry could be driven by hydrothermal vents. Such a biosphere would be utterly independent of starlight, an ecosystem founded on chemosynthesis and geothermal heat, huddled in profound darkness around the ultimate gravitational anchor. While the probability of such a system existing is infinitesimally small, the mere conceptual possibility expands the habitable zone in our imaginations from the narrow band around stars to the most remote and dark gravitational wells in the galaxy, suggesting that life, if it is sufficiently versatile, could find a way in the most unexpected of abysses. On a more fundamental physical level, the continued study of isolated black holes offers a potential testing ground for the no-hair theorem, a cornerstone of classical general relativity, which states that a stationary black hole is completely described by just three externally observable parameters: its mass, its electric charge, and its angular momentum, spin. All other information about the matter that formed it or has fallen into it is lost, disappearing behind the event horizon, hence the phrase, "black holes have no hair." For an isolated black hole, the spin is particularly difficult to measure. In binary systems, spin can be inferred from the properties of the accretion disk or from the detailed waveform of gravitational waves during a merger. For a solitary black hole, its spin could, in theory, be measured through its subtle influence on the space-time curvature around it, which would affect the paths of light during a microlensing event in a minute way. Detecting such an effect is far beyond our current capabilities, requiring astrometric precision orders of magnitude greater than currently possible. However, future generations of space-based interferometers, or incredibly long baseline optical telescopes, might one day discern the signature of frame dragging the twisting of space-time around a rotating mass, around a lensing black hole. A confirmed measurement of an isolated black hole spin would not only test the no-hair theorem, but also provide clues about the angular momentum of its progenitor star, locked away and preserved in the vortex of the singularity. Finally, the discovery resonates with a deeper, almost philosophical strand of astronomy, the pursuit of the unseen for its own sake, the mapping of the invisible architecture of reality. For most of human history, the night sky was a canvas of points of light. We have learned that the spaces between those points are not empty, but filled with gas, dust, planets, asteroids, comets, and now we are confirmed in our suspicion that they are also threaded with dark, massive knots of spacetime. This changes our perceptual relationship with the cosmos. To look up at the Milky Way band is to look not only at a river of stars, but to gaze through a field littered with gravitational tombs, moving silently through the void. Each of these black holes is a place where the normal rules of space and time have come to an end, a puncture in the fabric of the universe that is nonetheless seamlessly woven into the galactic gravitational field, affecting the motions of everything around it. They are the ultimate examples of how mass shapes the cosmos, independent of light. Their study forces us to conceive of the galaxy not as a collection of luminous objects, but as a fluid of mass, with density fluctuations, both bright and dark, all contributing equally to the gravitational potential that holds the grand structure together. In this view, stars are merely the visible peaks of the mass distribution, while black holes are the deep, dark troughs, both equally real, both equally shaping the cosmic landscape. The wandering black hole is our first clear step into that landscape's shadowed valleys, a guide into the darkness that compels us to learn to see in a new way, not with light, but with the subtle, inexorable geometry of gravity. As the narrative of this solitary wanderer expands from its specific detection to its broader cosmic context, we are drawn to consider its ultimate fate across timescales that stretch into the almost inconceivable future of the universe itself. Governed by the subtle quantum process of Hawking radiation, an isolated stellar mass black hole possesses a lifetime that is staggeringly long, proportional to the cube of its mass. For a black hole of 7 solar masses, this evaporation timescale exceeds the current age of the universe by a factor of 10 to the 57th power, a number so vast it defies analogy. It is a lifespan that will outlast the fusion epochs of all stars, the slow decay of galactic structures, and the era of stellar formation itself. It will persist long after the Milky Way has merged with Andromeda and other galaxies in the local group, after the resulting elliptical galaxy has aged and its stars have burned out or been ejected, after the cosmos has expanded and cooled under the relentless influence of dark energy, leaving galaxy clusters isolated in deepening void. Throughout these epochs, the black hole will continue its silent journey, now through a far emptier and darker environment, its gravitational influence perhaps the only organizing principle for any stray particles or dark matter in its vicinity. Its eventual demise, trillions upon trillions of years in the future, would be a faint, final burst of particles as it reaches the final stages of evaporation, a quiet pop in an otherwise silent and dark cosmos, an end as understated as its long existence. In this distant epoch, it might be one of the last macroscopic structures of the stelliferous era, a relic from a time when the universe was bright and filled with stars, persisting as a dark monument almost to the very end of time. Yet, on shorter, but still profoundly long timescales, the environment through which it travels will undergo radical transformation. And with that, the nature of its interactions may change. As the galaxy evolves, the density of the interstellar medium will decrease as gas is locked into stars and stellar remnants, and as supernovae and stellar winds eject material into the galactic halo. The Wanderer's passage will become ever more frictionless, its accretion of even tenuous hydrogen gas dwindling to truly negligible levels. However, its gravitational role may become more pronounced in a different way. In the far future, as stellar velocities gradually relax through dynamical interactions, the galaxy's structure will become more diffuse. A black hole, with its concentrated mass, can act as a gravitational seed, a focal point that can slowly, over billions of years, gather a loose cluster of older, lower mass stars or stellar remnants around itself through a process known as dynamical friction. While this is more likely for more massive black holes, even a 7 solar mass object could, given enough time in a relatively dense region of stellar corpses, become the nucleus of a small, dark cluster of white dwarfs, neutron stars, and other black holes bound together by gravity, but emitting almost no light. This would be a slow, cosmic reversal of its natal ejection, a gradual return from solitude to being the heart of a dark, skeletal system, a congregation of the dead drawn to the deepest well of gravity among them. Its long loneliness would thus be a phase, not a permanent condition, a testament to the patient, persistent power of gravity to build structures across aeons, even from the darkest of foundations. The discovery also reframes our understanding of the local interstellar neighborhood. The confirmation that such an object exists and is detectable implies that our solar system, in its orbit around the galactic center, has likely passed within a few light years of such dark wanderers numerous times over its 4.6 billion year history. Each passage, while leaving no dramatic geological or climatic imprint, would have subtly altered the gravitational boundaries of the Oort cloud, perhaps triggering minor comet showers. The cosmic history of our immediate vicinity is not only written in the light of stars we see, but in the unseen gravitational perturbations of passing dark masses. This introduces a new, faint background of gravitational noise into models of the solar system's long-term dynamical evolution. While the effects are minuscule and overwhelmed by other factors like the galactic tide and passing stars, they are a reminder that our island of light exists within a sea that contains not just other islands, but also deep-moving trenches of pure gravity. Our planetary system has been, in a sense, sailing through a graveyard of stellar remnants, its course ever so gently nudged by the ghosts of long-dead stars. On the frontier of detection technology, the pursuit of more wanderers drives innovation. The next leap will likely come from the combination of extreme precision astrometry with the power of machine learning algorithms designed to sift through the gargantuan datasets of time domain surveys. Algorithms are being trained to identify the characteristic, smooth, symmetric brightening of a microlensing event amidst the noise of variable stars, supernovae, and instrumental artifacts. They can also flag events with unusually long durations, or with astrometric signatures in preliminary data, prioritizing them for precious follow-up time on space telescopes. Furthermore, the simultaneous analysis of data from multiple surveys, OGLE, MOA, KMT-net, the future LSST, and Roman, will allow for real-time alerts and rapid response observations. This global, automated, intelligent network of telescopes will form a sort of nervous system for the galaxy, sensitive to the faintest twinges of gravitational lensing, capable of tracking the movements of dark matter in near real time. The first isolated black hole was found through a combination of skill and serendipity. The next 100 will be found through a deliberate, engineered process, a systematic census of the dark, This transition marks the maturation of the field from discovery to demography. In a final, reflective turn, the existence and now the confirmation of these solitary black holes offer a profound metaphor for the scientific process itself. Science often advances not by studying the brilliant and obvious phenomena, but by investigating the anomalies, the quiet signals, the empty spaces where theory predicts something unseen should reside. The decades-long search for dark compact objects through microlensing was a pursuit of a predicted shadow. It required faith in the predictive power of theory Einstein's relativity and the patience to collect data, year after year, looking for a signature that might not appear. The discovery validates that slow, cumulative, and often tedious work. It is a triumph of indirect evidence, of building a compelling case, not from a direct image, but from a confluence of meticulous measurements, the light curve, the astrometric shift, the deep non-detection in infrared and optical bands. In an age where spectacular images from JWST and Hubble capture public imagination, this discovery reminds us that some of the most fundamental truths of the cosmos are revealed not in glorious portraits, but in painstakingly assembled forensic evidence, in the whisper of data that tells of an unseen presence. The wandering black hole, in its elegant isolation, thus becomes a symbol for the hidden truths that await discovery, not in the limelight, but in the quiet, dark corners of data, requiring us to develop new senses and new methods to perceive the profound realities that shape our universe. Bridging the gap between the cold, deterministic physics of general relativity and the warm, uncertain realm of biology, the concept of the wandering black hole invites one last expansive consideration: its potential role, however speculative, in the grand narrative of cosmic evolution and complexity. In the conventional story of life's rise, energy flows from stars to planets, driving chemistry and biology. But if we allow our definition of a habitable environment to extend to any setting with a persistent energy gradient and a liquid medium, then the gravitational field of a black hole becomes a potential engine, albeit a cold and dark one. Tidal forces on a captured rocky body could provide internal heat through friction, maintaining a subsurface ocean for billions of years, far outlasting the main sequence lifetime of any star. Such a world, adrift in the galactic darkness with its black hole sun, would represent an experiment in biology, utterly divorced from photosynthesis. An ecosystem based entirely on chemosynthesis and geothermal energy, its timescales dictated by orbital mechanics and tidal heating models, rather than stellar evolution. The emergence and evolution of life in such a system would follow a trajectory unimaginably different from our own, potentially leading to forms and senses adapted to perceive gravitational waves, magnetic fields, or the subtle infrared glow of radionuclides rather than light. While the probability of such a system existing is vanishingly small, its theoretical possibility expands the canvas of biological potential in the universe, suggesting that the conditions for life are not exclusive to the Goldilocks zones of stars, but could persist in the most profound and permanent gravitational wells, where the stability is measured in trillions of years, offering time for evolution to explore possibilities on a scale that makes the age of Earth seem but a fleeting moment. From this biological speculation, we return to the astronomical present, where the discovery of the Wanderer has already begun to influence the design of future missions and theoretical frameworks. The success of the astrometric microlensing technique has cemented its place as a primary tool for the Roman Space Telescope's galactic survey. Mission planners now have a proven detection in hand, allowing them to refine their sensitivity estimates and optimize their observing strategies to maximize the yield of isolated black holes and other dark compact objects. Furthermore, the event has provided a crucial benchmark for simulations of galactic populations. Numerical models that track the birth, evolution, and dynamical scattering of stellar remnants can now be calibrated against a real, clean data point. These models, which incorporate initial mass functions, supernova kick mechanisms, and galactic dynamics, can be tuned so that their predicted detection rates for Roman and LSST match the reality of this first discovery. This iterative process observation informing simulation, simulation guiding future observation, is the engine of scientific progress. And the wandering black hole has become a key gear in that engine, turning our theoretical understanding of the galaxy's dark component from abstract prediction into a quantitative, testable science. The philosophical resonance of the object deepens when considered alongside other great astronomical mysteries, particularly the nature of dark matter. While stellar mass black holes are ruled out as the primary constituent of dark matter, their abundance and formation history do not match the required cosmological profile. Their detection via gravity alone demonstrates a principle. If you cannot see it, you can map it by how it bends the light of things you can see. This is precisely how we map dark matter on cosmological scales, through weak and strong gravitational lensing of galaxies and the cosmic microwave background. The solitary black hole is a miniature, nearby, and perfectly characterized example of this universal principle. It is a tutor in the methods of dark matter astronomy, a scaled-down laboratory where we see the technique work with stunning clarity on a single, dark mass. Studying it hones our skills for the far more complex task of mapping the diffuse, clumpy, and invisible dark matter halos that govern the fate of galaxies and the large-scale structure of the universe. In this light, the Wanderer is not just an object of study, but a training ground for our collective comprehension of the unseen 95% of the cosmos that remains mysterious. As the story of this specific black hole reaches its conclusion in our narrative, its physical journey, of course, continues unabated. At this very moment, as these words are formed and read, the object moves through its section of the galactic disk, its immense gravity silently curving the paths of interstellar dust grains, and the occasional cosmic ray. Somewhere, perhaps centuries from now, its path will again align almost perfectly with a distant star, and another microlensing event will begin a slow brightening that will be captured by the watchful instruments of a future civilization, who will trace its astrometric shift with even greater precision, refining its mass and velocity, perhaps detecting the faint whisper of its spin. It will be rediscovered, its lonely voyage documented once more, a celestial lighthouse whose beacon is not light but gravity, flashing on a timescale of millennia. It is a permanent part of the galactic fabric, a stitch in the dark tapestry of the Milky Way, now known to us, but forever indifferent to our observation. In the end, the tale of the wandering black hole is a tale of perspective. It teaches us to see the cosmos not as a static picture, but as a dynamic, multi-layered sculpture in space-time, where mass is the true sculptor and light is merely one of its tools. It challenges our reliance on emission and reflection, urging us to become detectives of geometry, readers of distortion. It humbles us with the scale of its solitude and the longevity of its existence, reminding us of our fleeting moment in the cosmic drama. And yet, it also elevates us, for with our mathematics, our technology, and our patient curiosity, we have reached out across 5,000 light years and touched the untouchable, measured the immeasurable, and found a profound silence that speaks volumes about the nature of gravity, stars, and the hidden architecture of our galaxy. The black hole that wanders alone is no longer entirely alone. It is now observed, studied, and pondered. In the act of discovering it, we have formed a connection, a one-sided, intellectual, but deeply human connection with one of the most isolated entities in the universe, drawing it from the realm of theoretical prediction into the shared light of our understanding, even as it itself remains forever in the dark. The legacy of this discovery extends beyond the confines of astrophysical journals and into the broader cultural and philosophical dialogue about humanity's place in the cosmos. For centuries, black holes have occupied a shadowy realm in the human imagination, symbols of ultimate mystery and existential dread. The confirmed existence of one drifting in isolation, a solitary leviathan in the galactic deep, refines that symbolism. It is no longer merely a destructive monster at the center of a system or a distant abstraction. It is a specific, localized phenomenon with a measurable trajectory, a quiet neighbor in the vastness. This demystification through precise measurement does not diminish its awe. Rather, it transforms the awe from one of fear of the unknown to a profound respect for the intricate, knowable laws that govern even the most extreme objects. The wandering black hole becomes an emblem of the power of scientific inquiry, a testament that through patience, ingenuity, and rigorous thought, we can illuminate even the darkest corners of creation. It reminds us that the universe is not designed to be comprehensible, but that it is comprehensible nonetheless, and that each act of understanding, each measured deflection of starlight, is a small victory of reason over chaos, a gentle light cast into the abyss. The narrative of this object also weaves into the ongoing story of cosmic evolution on the grandest scale. In the far, far future, under the cooling glow of degenerate stellar remnants and the stretching influence of dark energy, black holes may become the last significant structures in the universe. After protons decay and brown dwarfs evaporate, after galaxies have dissipated and the cosmic background radiation has redshifted into oblivion, black holes will remain as the final custodians of mass and order. Isolated stellar mass black holes, like the one we have found, will be among the longest lasting of these relics. Their slow evaporation via Hawking radiation will be one of the last remaining processes injecting energy into an otherwise cold, dark, and nearly empty cosmos. In that distant epoch, the universe's history will be written not in light, but in the gradual dimming of these gravitational beacons and the faint pops of their final evaporation. Our detection of this wanderer is, in a sense, a glimpse of that ultimate fate, a preview of a universe where gravity is the last story left to tell, and where objects like this are the final, silent narrators. It connects our present, vibrant, stelliferous era to the cold, dark eternity that lies ahead, providing a tangible link in the great chain of cosmic events that stretches from the Big Bang to the final evaporation of the last black hole. On a more practical level, the techniques honed in this discovery are already being applied to new puzzles. Astronomers are now searching for similar astrometric microlensing signatures caused by other elusive populations, free-floating planets, especially those in the Earth to Neptune mass range, primordial black holes, hypothetical remnants from the dense early universe that could be of any mass, and even dense clumps of dark matter, should they exist. The data pipeline established from wide-field survey detection to high-precision space-based follow-up is now a proven pathway. Each new type of dark object will have its own signature. The duration of the lensing event hints at mass. The shape of the light curve can reveal if the lens is a binary, and the astrometric shift confirms the compactness and darkness. The wandering black hole was the first clear signal through this pipeline, but it has opened the channel for a symphony of other, fainter signals to be discerned. We have learned to listen to a new frequency in the cosmic static, and now we can begin to distinguish the different notes within it. Furthermore, the discovery underscores the critical importance of long-term, foundational science projects. The microlensing surveys that found the event, OGLE and MOA, are not flashy, high-profile missions, but decades-long, persistent monitoring programs. They represent a different kind of exploration, not a sprint to a specific target, but a patient, systematic mapping of the sky. This discovery is a fruit of that patience, a reward for the commitment to collecting data night after night, year after year, without any guarantee of what might be found. It is a powerful argument for the support of such foundational, curiosity-driven science, for it is in these vast, systematic datasets that the rarest and most surprising treasures are often buried. The wandering black hole did not announce itself. It had to be unearthed from years of careful observations, a diamond hidden in the rough ore of petabytes of stellar brightness measurements. This model of discovery, slow, cumulative, and driven by systematic survey, is likely to dominate the next era of astronomy as we move from studying individual cosmic wonders to understanding the statistical properties of the universe as a whole. Finally, the story of this black hole brings us back to a simple, profound fact. It is out there. It is a real object with real properties moving through real space. This fact, mundane in a scientific sense, is extraordinary in a human one. We live on a small rock orbiting a middle-aged star in the quiet suburbs of a spiral galaxy. Yet from this vantage point, we have developed the intellectual and technological tools to detect a completely dark sphere of warped space-time, weighing 7 times our Sun, passing through the distant reaches of our galactic home. We have measured its mass, its distance, its speed, and we have deduced its violent birth and its likely eternal future. This act of cosmic connection, bridging the gap between our fragile biological consciousness and the most austere gravitational phenomena, is a triumph not of technology alone, but of the human spirit's relentless drive to understand. The black hole wanders alone, but in knowing it, we have, in some small way, ended its absolute solitude. We have brought it into the circle of our knowledge, made it a part of our story of the universe. And in doing so, we have expanded the boundaries of that story, reminding ourselves that the cosmos is richer, stranger, and more full of hidden wonders than we could have possibly imagined, and that there are always new ways to see, even in the deepest dark. The quiet saga of the wandering black hole thus finds its resolution not in an ending, for the object's journey is eternal, but in the opening of a new chapter of cosmic perception for those who observe it. As the data settles into the annals of science, it leaves behind a transformed landscape of possibility. The galaxy is no longer merely a collection of stars we see. It is a dynamic mass distribution, a fluid where luminous points are interspersed with dark, moving concentrations of gravity that are now knowable. This shift is profound. It means that when we gaze at the Milky Way's shimmering band, we can consciously perceive the invisible architecture within it, the countless solitary black holes, the rogue planets, the neutron stars, all drifting like dark ships on a luminous sea, their presence now confirmed not as fantasy, but as fixtures of the galactic ecosystem. This enriched perception is the true gift of the discovery, a new layer of reality revealed through the marriage of theory and meticulous observation. The path forward is illuminated by this success. The Nancy Grace Roman Space Telescope will soon begin its Galactic Bulge Time Domain Survey, a mission designed to capitalize directly on the methodology proven here. It is expected to discover hundreds of similar isolated black hole events, building a statistical sample that will answer the lingering demographic questions with authority. Each new detection will be a thread in a larger tapestry, weaving together a coherent picture of stellar death, supernova kicks, and galactic dynamics. Astronomers will not only ask if these objects exist, but how many, of what masses, moving with what velocities, and distributed in what patterns throughout the galactic disk and halo. This transition from the singular to the statistical marks the maturation of the field. The wandering black hole ceases to be a curiosity and becomes a standard candle of darkness, a well-understood class of object that serves as a tool for probing the galaxy's history and structure. Its solitude becomes a feature that makes it a clean probe, uncomplicated by the messy physics of binary interactions or accretion disks. On a broader canvas, the principles of gravitational lensing that allowed this discovery continue to be our most powerful tool for mapping all unseen mass in the universe, from the halos of dark matter surrounding galaxies to the large-scale structure of the cosmos itself. The precise measurement of an isolated stellar mass black hole is a miniature, local, and exquisitely controlled demonstration of the same physics that governs the bending of light from distant galaxies by foreground clusters. It is a validation of the underlying relativistic framework on a scale that is both comprehensible and astonishing. By mastering this technique on nearby subtle events, we refine our ability to apply it to the most monumental scales, ensuring that our maps of dark matter and our models of cosmic evolution are built on a foundation of empirically verified precision. The Wanderer, in its quiet way, has calibrated a key instrument in the toolbox of modern cosmology. And so, we return to the image with which we began, a shape of perfect nothingness moving through the interstellar dark. It is still there, a permanent part of the galactic fabric. Its gravity continues to bend the paths of passing photons with imperceptible grace. It does not know of the flurry of scientific papers it inspired, the observing time on Hubble it commanded, the simulations it calibrated, or the human minds it captivated. It simply is a natural consequence of a star's death, a knot in space-time, following the curve of its geodesic. But for us, its meaning has been utterly transformed. It is no longer just a prediction of relativity or a subject for theoretical speculation. It is a known entity, a character in the story of our galaxy, with a documented history and a projected future. We have, in the most respectful sense, made its acquaintance. In the grand, slow narrative of the universe, where events unfold over billions of years and distances stretch beyond comprehension, human science is a fleeting, brilliant spark. Yet, in that spark, we achieve something remarkable. We extend our consciousness outward. We map the void. We find patterns in the chaos. And we connect with phenomena utterly alien to our experience. The detection of the wandering black hole is a pristine example of this achievement. It required us to think in terms of geometry rather than light, to be patient across years of observation, and to trust in the predictive power of mathematics. It is a story not of sudden revelation, but of gradual, cumulative understanding, a story that mirrors the slow, drifting journey of its subject. In the end, the greatest lesson of the black hole that wanders alone may be this: that the universe reveals its deepest secrets not to the hurried or the loud, but to the calm, the persistent, and the deeply attentive, who are willing to listen for the subtle distortions in the fabric of reality and to follow them, no matter how dark the path, into a fuller understanding of the magnificent cosmos we inhabit.